Okay, hello class. Let's continue to the second part in this chapter. Okay, previously we covered the concept of chemical potential. What is the definition of chemical potential? You know that chemical potential is equal to dou G over dou, or due to the composition or mole composition change at constant temperature, pressure, and also the other species or the composition for others. And we also have learned about the partial properties or partial properties. Example for the overall general thermodynamic properties for the species I equal to dou over the exchange of the general, okay, I put the general thermodynamic properties due to the change of the composition at constant pressure, temperature, and the other species then exchange in the for the respective species. So by comparing this, we can say that the chemical potential is equivalent to the partial properties, since we use the Gibbs energy, so it refers to the partial molar Gibbs energy for the species I. And then we also covered on the Gibbs-Duhem energy. Okay, how we rearrange the equation to relate with the chemical potential. From the previous study, we also covered the introduction of the fugacity. Okay, fugacity is the replacement on the limitation of the chemical potential, which is, example, in the system, the chemical potential for the species will be the same, but the fugacity will be adjust the pressure to obtain the value. We can obtain the value of fugacity are different for each species or for each phases. In this part, you will learn about the fugacity and fugacity coefficient in pure species. You should be able to determine or relate to the vapor-liquid equilibrium and also in the pure liquid. And the second topic, we will cover the species or how to determine the fugacity and fugacity coefficient if relate to the species in the solution. Okay, in determining this fugacity of the species in the solution, we're gonna use equation or state. We stick to the referring to the value of pressure given in the question or in the problem. If we have lower pressure, that means less than 15 bar, you can use the Virial equation that introduce the constant of B and B prime and B naught. And also you may refer to the Lee-Kessler if the pressure is higher than 15 bar. Or Lee-Kessler, that's mean you need to refer to the reference table to determine the coefficient, fugacity coefficient node and fugacity coefficient one, that gives you the value of fugacity of the species in the solution. And last topic is relate to the ideal solution. You should be able to determine or understand the concept of ideal solution and relate it with the access property, which we will discuss more on the Lewis-Randall's rule. Well, let's move to the introduction of the fugacity. Okay, the fugacity is the thermodynamic drive for molecules to escape from one phase to another. Basically, the fugacity is the measurement of the chemical potential by adjusting the pressure. Okay, example, we have this chemical potential against the pressure. Okay, these are the ideal gas or the data for the ideal gas, and we have this data for the real and line for the ideal gas. Okay, you can see we have this. If the pressure or the fugacity is lower than the given pressure, that means it attracts the dominant or it tends to escape from this from this in the system. I mean, escape from one phase to another. Or we also can, or if has higher than pressure, that's mean it has the repulsion dominant. Okay, the fugacity, the relation of the fugacity and pressure can be determined the fugacity coefficient. If we determine the fugacity is less than 1, that means gas has more attraction and less tendency to escape. If higher than 1, that means it less attraction and more tendency to escape. That means the molecule or gases is not attract each other and it tends to be escaped. And then if the fugacity coefficient is equal to 1, and then we're gonna have an ideal gas. That means we have the same, the real is mimic to the ideal gas. Okay, we will learn more about the fugacity and also fugacity coefficient in the next slide. Okay, to derive the equation, okay, it relates to the pressure. Okay, example, if in the system we have the two-phase or maybe liquid and vapor. So we have two-phase liquid and vapor. Okay, the Gibbs energy or given by dg equal to VdP minus SdT. Okay, since the Gibbs is a generating function, so most of the correlation of the thermodynamic properties will be based on the Gibbs energy, or most on the equation or expression created in this module will be referring to the Gibbs energy. Okay, at constant temperature, so it turns to dg VdP. For the ideal gas, we have dg ideal equal to VdP. So as we know that PV RT, so V equal to RT over P. So it turns to RT over P dP, or we also can rearrange dP over P, and then we can perform the loan. That's mean the dg ideal equal to RT d ln P. So for the real gas or dg real, the term of P is changed to the fugacity, because we have this to differentiate between the real and ideal gas. Okay, by comparing between the ideal and real gas, so D, we have G real minus G ideal, it gives the RT F ln P, or you can rearrange it, it turns to ideal over RT, and we can have this D ln F over P. Okay, D ln F over P here, okay, can be known as fugacity coefficient. Fugacity coefficient is determine or describe the ratio of the real gas to the ideal gas. Okay, if we have a constant, or we have the constant P, so that means we have P equal to 0, D ideal equal to D G real, or we can obtain the F equal to P. So if we rearrange the equation of F over P, so we can get the by comparing the or determine the based on the P at constant temperature. So we can get Z1 over PD. So this is once we perform the arrangement that this is for the ideal, and then for the real we can have PV Z RT, or for the real is ZRT over P. So you can insert this to this equation, or finally we can have Z minus 1 P over P at constant. This is at constant temperature. So let's move to the next. Okay, the main purposes of this equation is to show to you how can we obtain the fugacity and also the fugacity coefficient. Okay, the fugacity and fugacity coefficient is can be described based on the real and ideal gas by introduce the integration constant at, or known as integration constant, which is at constant temperature. Okay, the species dependent function on the temperature only. Okay, for the real system, it also analogous to the ideal gas, which is we introduce the fugacity into the equation, or I is represent to the species. Okay, the ideal solution, we have the integration constant plus RP ln P. And then for the real fluid, we have the replacement of the pressure to the fugacity. And then the unit is still, the unit of fugacity is still in pressure. And then when we compare or differentiate between the real and ideal gas, so that's what I described previously. So we can have or we introduce the fugacity coefficient in the system. So the unit should be dimensionless, right? Because if we have bar and pressure also bar, so it has a dimensionless unit. Okay, for the ideal gas, or the fugacity coefficient equal to 1, that's give the fugacity equal to the pressure for ideal gas. Okay, and then for the first topic, the fugacities of the pure species in the vapor liquid equilibrium. Okay, so we have this the expression for the real system. Okay, and if the system having two phases, example vapor and liquid, okay, this we can denote the symbol of phases at the fugacity, and then comparing between the liquid and vapor phases, so it gives us 0, a value of Gibbs, and equal to, okay, we can have this expression, and then by solving, finally the fugacity for the vapor equal to the liquid and also the saturation. Or also we have the fugacity coefficient for the vapor equal to the fugacity coefficient for the liquid, and also we call as the saturation, or saturation fugacity coefficient equal to the fugacity saturation over the pressure at saturation. Okay, for the pure species coexisting liquid and vapor phases are in equilibrium. They have the same temperature, pressure, and fugacity. Okay, next we move to the fugacity of pure liquid. Okay, pure liquid, you may refer to the region or to the diagram of pressure, volume, molar volume diagram, PV diagram. The region of the liquid is between this area, which we have the region for the liquid, and then this is region for the vapor. Okay, if we have this is the critical line, and then we also have the vapor and liquid region. So for the liquid region, example, we have at a certain pressure, so it will move to the saturation pressure or still under the liquid region. Okay, at constant temperature. Okay, so since the system is is applied at constant temperature, so we have dG equal to VdP. By integrate it, so we can have the G at this point to the G at saturation, and then we can compare with the previous VLE that we obtained. So we can have this expression or ln fugacity of the species over fugacity of the species at saturation equal to 1 over RT of VdP. And then we can obtain this equation by rearrange it, and then we can finally obtain the value of F1 or value of the fugacity of species 1 in the liquid. So the fugacity of the saturation equal to the fugacity coefficient at saturation times the saturation pressure. And once we rearrange, we can obtain this equation or this term known as the Poynting factor, or V is determining from the Rakat equation. You can obtain this from the Rakat equation. So you need to determine example VC equals, or we will refer to the example later for you to be more understand about this. And then, okay, let's take a break. What is the difference, okay, based on the Gibbs energy expression between real and ideal gases? Okay, to express the Fugit, to relate comparing between the real and ideal gases. Since the topic is related to the fugacity, so you can obtain the what is the expression for the Gibbs energy between the in the real and also in the ideal and also the real gases. Okay, let's take a look on the example for you to be more understand about how to determine the fugacity in the liquid, vapor, and also the vapor phase, okay, or relate to the pure species. Okay, first question, calculate the fugacity of a pure gas at 500 K and 30 bar. Second, supposedly the pure liquid is in equilibrium with the gas at 500 K and 30 bar. Calculate the liquid fugacity. So this is the we need to determine the fugacity in vapor, and the second is the fugacity in liquid. So the term is equilibrium here. Okay, the third question is calculate the liquid fugacity in liquid at 500 K and 60 bar. So the first, the given pressure is 30 bar, and then the second is 60 bar. All the information is given. So let's proceed to the A first. So for the A, we need to determine the fugacity in vapor. So fugacity in vapor, the given temperature is 300 Kelvin, pressure is 30 bar. So what is the information given? So we have Z1. So let's extract all the information first. 0.01 P. And then whereas this, okay, P is, Z is for this, P0 to 30 bar. So how can we determine? Okay, we know that the ln F over P, if you may refer to the derivative equation that I explained previously. So ln F over P, 0 P Z minus 1 over P dP. Okay, this equation is valid at constant temperature. So you may use this equation to determine the fugacity in the of the species or in the pure species at constant temperature. So pressure, so we need to first rearrange it. Z minus 1. So first, this is the equation can be applied. Second, to rearrange. So Z equal to 1 minus 0.0 P, or Z minus 1 equal to minus 0.0 P. And then you can insert into this. So ln F over P equal to 30 bar. So Z minus 1 minus 0.0 P E D E. So we can solve this. So first P can be cancelled. Cancel P, or I should put 1. Then I can cancel P. So it gives this 30 minus 0.01 dP. So P, okay, we have, okay, and then we can solve this part. So 0.1, 30 minus 0, so it gives the answer is 0.30. So ln F over P is minus 0.30. So ln F 0.30. So the pressure is 30 bar. And then you can have F is exponent times 30 bar. So the answer is 22.2 bar. So we can obtain the fugacity or fugacity gas at this condition is 22.2 bar. Okay, next question is need to determine the fugacity in or the liquid fugacity if the system in equilibrium. So if the system is in equilibrium, so we have the fugacity of vapor at 22.2 bar. If at equilibrium, so the fugacity in vapor equal to the fugacity in liquid equal to 22.2 bar. And then we can move to the next question. Calculate the liquid fugacity. Okay, then temperature is 300 Kelvin. Pressure is 60 bar. So we need to determine the fugacity in liquid. What's the fugacity in liquid? So back to the pure liquid in this equation. F equal to, okay, we may use this equation. F equal to F liquid, F saturation, exponent P L P minus P saturation over RT. Okay, so we can obtain the PF, okay, F saturation. So we have the value equal to 22.2 bar exponent. Okay, VL also given 25 cm triple mole. Then we have pressure at 60 bar minus saturation pressure is 30 bar over RT. So we can use this M3 bar over mole K. And then the temperature is 300 Kelvin. So you may check the unit first. So bar mole cm bar. Okay, should be okay. And then the answer is 22.2 times 10018. So it gives around 22.2 bar. Okay, this is how we determine the fugacity based on the problem given. So for the C, or the question of C, the liquid fugacity can be determined using the Racket equation, or we have the expression of this pointing factor in this equation. Okay, let's move to the fugacity and fugacity coefficient for the species in solution. Okay, for the ideal gas, okay, we have the expression of integration constant plus RT ln P. And then when we compare or introduce the chemical potential that relates to the partial Gibbs or ideal gas, so we can replace the pressure to the partial pressure at partial, or the PR, and P equal to, or the partial pressure equal to the pressure times the composition in vapor, since this is an in gas state. So the equation is turns to the, if relate to the chemical potential equal to the integration constant plus RT ln the partial pressure. And for the real gas, it turns, or we can replace it to the fugacity. Okay, the cap symbol is for the species in the solution, or I is for the we can say it is I is the for the species. Example, if you have species for the species 1, or the species in the solution, or the species 2, and etc. So cap here for the species in the solution. And then if the species in the solution have a different phase, so we denote by example alpha and beta. So by comparing it between the phases, so we can have this expression. And then we can say that the fugacity of the species in the solution, regardless for any phases, it will have the same value. Okay, let's take a look on the fugacity coefficient. Previously, we already covered the fugacity in the vapor liquid equilibrium. How about the fugacity coefficient? Okay, for the ideal gas, okay, we have the partial pressure, and then we move to the real gas. So we have the real gas is defined, or replace it with the cap of the fugacity for the species, or the fugacity of the species I in the solution. And then when we compare it between the real to the ideal gas, it gives us the residual. So we have the residual, and also, okay, this give us the fugacity of the species in the solution. So we can obtain the fugacity coefficient from this difference of the between the real and ideal. Okay, for the ideal gas, Gibbs energy is equal to the 0. And then when it also, for the ideal gas, we know that the activity or the fugacity coefficient is equal to 1. And then we can have this another term, that the fugacity in ideal gas of the species in the solution equal to the partial pressure. So we have another correlation that we can further explain about this later. Okay, and then we move to the determination of the fugacity coefficient of the species in the solution. Okay, it can be determined using the equation of state. Okay, the equation of state can be divided by cubic equation and generalized equation. Okay, but we will use the generalized equation either by using the virial equation or Lee-Kessler. Okay, the virial equation can be chosen if the pressure is lower, or if we have higher pressure, that means higher than 15 bar, we can choose the Lee-Kessler or refer to the fugacity coefficient of node and 1 in the from the table. Or for the virial equation, you can use this equation to obtain the fugacity coefficient by determining the B node and B1. So the eccentric factor also you may refer to the table or reference table. For each species, it has own eccentric factor. And then you can obtain the TR from TR equal to T minus TC and PR equal to P minus P over PC. Then finally, you can obtain the fugacity coefficient. Okay, maybe we can take a look on the example to be more clearer about this. Okay, in determining the fugacity coefficient by using the virial equation. So we have this whether having the pure species or binary gas. So for the binary gas, you may have this cap, that's mean the species in the solution. And then for the pure species, we have this only the denotes by the theta. So we can obtain the fugacity or the theta of fugacity coefficient from this virial equation or by determining the B node and B1. So first you need to determine or find the value of TR, and then after that you can insert into this table. So I think that better we will better if we move to the example to perform the calculation if using the virial equation. Okay, these are the details if we are using if we use the Lee-Kessler. Lee-Kessler, that means the pressure is higher than 15 bar. So if we have a multi-component, so you may need to determine first the composition, which usually is given, and then the eccentric factor may be referred from the table, and then this also can be referred from the table, and then finally you can obtain the value for each for all the composition by multiply it with the composition, and then you can proceed to the calculation of to determine the fugacity coefficient. Okay, these are the tables to be referred: table 1 E13 and table E14. Okay, let's take a look on the example 3. Okay, estimate the fugacity for the following species. Okay, cyclopentane at temperature and pressure. Okay, the vapor pressure, that's mean P saturation of cyclopentane is 5.267. Okay, the information given is you can obtain the region of the cyclopentane. So if we have the pressure is less than P saturation, so or not less or higher than P saturation, so that's mean the region in compressed liquid. So actually you can obtain the region of the species that leads to you to choose the equation in calculating the fugacity. Okay, for the second question, isobutane at 120 degree and 64 bar. And 120 degrees Celsius, the vapor pressure, okay, P saturation also given at 25.83 bar. or this is the P. So this you may refer to this restriction to describe the region for that species. So P is higher than P saturation. So we can conclude this is the still in the compressed liquid. So for the compressed liquid, you may refer to the equation related to the Rakat equation and Poynting factor. And then also, how can you decide whether use the virial equation or the Lee-Kessler? So you may refer to the saturation pressure. At lower pressure, you may choose the virial equation, and at higher pressure, you can choose the Lee-Kessler. So let's pause a bit, and then you can try it by your own first. And the answer is given. The answer is given for both questions. So you may compare with your calculation, and then later I will show you the detailed calculation to solve this problem. Okay, I hope you already try it by your own first, and then let's take a look on the solution. Okay, for the question or for the A. Okay, let's first list everything or extract all the information. Since P is higher than P saturation, so the species in compressed liquid. So you may calculate the fugacity using this equation. The P saturation is given, and then the okay, you need to determine the volume in liquid. Okay, P is given, T and R also given. And the next step is to determine all the unknowns value. Okay, so to calculate the fugacity coefficient, so you may refer to the P saturation first. Since this is a lower pressure, so we use the virial equation. So we need to determine the B naught and B1 before inserting into the equation. Okay, you may refer to the table B1 for cyclopentane to extract all the information, eccentric factor, critical temperature, critical pressure, the critical volume, and also the compressibility factor. Okay, so first we need to determine the reduced temperature and pressure, and then after that you can proceed to determine the B naught and the B1. So let me remove this. And then we can obtain the B naught using this, and then inserting the TR for both in a determiner B naught and B1. So you can obtain the theta or fugacity coefficient using this equation. So you may use this equation, and then finally you can obtain the fugacity coefficient. Okay, inserting the fugacity coefficient into this equation, and then you can, okay, what else we need is the vapor liquid or the specific molar volume at the liquid. So you can obtain this from the Rakat equation. Or Rakat equation is used to determine the vapor or the molar volume in liquid. Or you need to determine the you need to define the molar volume for the critical and also the compressibility factor. And then after that, we have all the information. Finally, we can insert into this equation to obtain the fugacity. So the answer is at 11.78 bar. So this is the answer. Okay, let's move to the next question to determine the isobutane at temperature 120, or the given pressure and saturation pressure also given. So first we need to define the phases for this species. So based on the restriction that P is higher than saturation pressure, so we can describe the species in the liquid region. We can determine the fugacity using this equation for the liquid. And then we need to determine the fugacity coefficient or the theta saturation. So referring to the equation, so in determining the theta or fugacity coefficient, we can either choose the variable of Lee Kessler. How can you decide it? So you may refer to the saturation pressure. Since the saturation pressure is higher than 15 bar, so you may decide using the Lee Kessler. So to determine the first is determine the theta of fugacity coefficient. So referring to the Lee Kessler table, we need to determine at the theta naught and theta 1. So in order for us to determine this, we need to obtain the value of TR and PR. So extract all the information in the table for the species of isobutane, or determine the eccentric factor, the critical temperature, pressure, molar volume, and the decompressibility factor. And then the next step is to determine the reduced temperature and pressure to be inserted in determining the theta naught and theta 1. Okay, so we can, by using the interpolation, or you can use your calculator to determine this value, interpolate this value, and then finally it gives you the final of this activity or fugacity coefficient. So this is the eccentric factor, and then you can insert all the value, and then finally you can obtain the fugacity coefficient. So we already defined the value of the theta or fugacity coefficient. The saturation pressure also given. So we have the value of pressure and also R and T. So how can we determine the molar volume? So since this is for the liquid, so you may use the Racket equation. By using the Racket equation, and then we can obtain all the unknowns of values, and then inserting all the value, and then it gives you the fugacity at 19.38 bar. Okay, we have another example. Is to determine the fugacity of isobutane as gas. So previously we determined the liquid fugacity, and how about for the gas fugacity? Okay, the given temperature and pressure. So we need to use whether the Lee Kessler or various. So you may refer to the pressure. So the pressure is higher than 15 bar. So you may decide of using the Lee Kessler. So you may try it by your own first before we can proceed to the detailed calculation, and before I can show to you how to solve this equation. So the answer also given to you. So let's take a break a while you solving this problem. Okay, how to solve this? First is extract all the information. So you may refer to the pressure. Okay, the given pressure is at 20 bar. So you can use the Lee Kessler for high pressure. And then to determine the Lee Kessler, that means we need to find based on the theta naught and theta 1. So it requires the information of TR or reduced temperature and pressure. So you may determine so extract all the information from table 1, because we require the value of eccentric factor and also the critical pressure and temperature to determine the reduced temperature. And then after that, you can determine the reduced temperature and pressure. And then we may insert using this TR, the value of reduced temperature and pressure to perform the interpolation or within the value of PR and TR to obtain the theta naught and theta 1. So you may refer to table 13 and table 14. Finally, you can obtain the fugacity, because we know that the fugacity over P, it gives you the activity or the fugacity coefficient, denotes by theta. So that's why we can simplify it, or we can easily determine the fugacity. Okay, let's test your understanding. How do you relate the pressure effect in calculating the fugacity and fugacity coefficient? Okay, so what is the expression? Also relate it with the pressure that having the fugacity and fugacity coefficient in the expression. Okay, so if you still not unsure about this, you may refer to the previous explanation. So what is the expression? This is the simple expression. So the answer is, okay, so the answer is fugacity over the pressure of the real to the ideal, we can obtain the fugacity coefficient. So you can obtain the value of the fugacity coefficient from this, the difference of this fugacity and the pressure. Okay, let's move to the next topic, ideal solution. Okay, ideal gas is a good model for gases, standard comparison with the real gas. Another useful model for the solution. So it called as excess property, or ME, excess property equal to the real or the actual minus the ideal solution. Or this is the comparison between the mixture of ideal gas and ideal solution. So for the ideal gas, or the composition is the simple denotes by Y, and then for the ideal solution is denoted by S. So you can we can use the based on the partial properties, or the summation or the partial properties, it gives us the value of the thermodynamic properties or the thermodynamic relation, and same goes to the ideal solution. And for each thermodynamic properties, it gives us different equation of the correlation. So these are the summary for each to describe the ideal gas and ideal solution for each properties. So we have the Gibbs, entropy, molar volume, and also the enthalpy. Okay, previously we discussed about the introduction of this, of the fugacity, or the in the species for the species in the solution to its composition and the partial pressure. So it can be described by Lewis Randall's rule. So for the any real fluid, okay, any real fluid, we introduce the fugacity into the expression, or integration constant or temperature constant plus RT ln the fugacity. And then if we refer to the partial properties of the gas, or it gives us the expression. And if relate to the potential or chemical potential for the real gas in the solution, so it denotes by, we have this the same term, but we have the different symbol for the species in the solution, or denotes by the fugacity or cap fug F for the species I. And then we can compare between the ideal and the real gases, and then we can have the expression of the Lewis Randall's rule. Okay, the Lewis Randall rule applies to all species in ideal solution at same temperature, pressure, and composition. Fugacity for each species in ideal solution is proportional. Okay, for in the ideal solution is proportional to the mole fraction of the fugacity. So we can obtain the fugacity coefficient by divided the fugacity in ideal gas to to the mole fraction. Okay, the fugacity of the species in ideal gas is equal to the fugacity coefficient in the pure species I at same temperature and pressure, because you can see here we have the same, the same or the equivalent as pressure. We know that the ideal solution is, or the ideal solution of the fugacity in species for the species I equal to its mole fraction. That's why we have the similar value for the ideal solution and also the pure species. Okay, and then we move to the excess properties. Okay, previously we have learned about the residual properties, which is the comparison between the actual to the ideal gas. Okay, the excess properties is analogous to the residual properties, but it based on the actual to the ideal solution. Okay, the ME or thermodynamic properties can be either, we can describe the properties based on the system or referring to your system, whether the molar volume, the enthalpy, the internal energy, entropy, or Gibbs energy. Okay, so this is the how we can compare between the excess property and also the residual properties. So the excess properties is also can be expressed using the partial properties, or if we have this partial properties or the excess partial properties equal to the partial properties of the species I to the, or the real actual species minus the ideal partial properties. Okay, the summary of the equation for the Gibbs energy and relate to its property is shown in this table. So the first column we have this thermodynamic properties in relation to the actual Gibbs, or the actual relation to the actual Gibbs. So we have the relation of the molar volume, the entropy, enthalpy, and the heat capacity. And the second is the relation related to the residual to the residual of heat. So the relation also listed here. And then last we have the relation of the excess property to the Gibbs excess property. So you may refer to this summary. So basically, no need to memorize all the equation. So this is just to show you the relation between its properties to the Gibbs energy, whether we have the actual, residual, and excess properties. Okay, since previously we comparing all the thermodynamic properties with Gibbs energy. Okay, for the excess property, we also will focus on the excess Gibbs energy and also its activity coefficient. Okay, for the real of the Gibbs energy, or the excess Gibbs energy, it denotes, we also introduce the fugacity, or for the species in the solution denotes by the cap for the species I. And then for the ideal solution, we introduce the SFI, which is equal to the defined or described by the Lewis-Randall's rule. The ideal solution of the fugacity of the species I equal to its mole fraction. And then when we compare between the ideal and the real, so we can obtain this or rearrangement, and then we can obtain the excess Gibbs energy. So we can obtain as the excess Gibbs energy, and we introduce the activity coefficient. Okay, actually we can also refer to the modified Roth's law, which activity coefficient is introduced into the equation. So for this activity coefficient in this Gibbs energy topic is referred to the fugacity of the species I in the solution of its mole fraction. And then we can determine the fugacity. Okay, we already determined the activity coefficient. And for the Gibbs energy, it can be also if the system is having the ideal solution, that's mean the excess Gibbs energy equal to 0, essentially the activity coefficient also equal to 1, and it gives back to the Lewis-Randall's rule. And then if the system, or we expand the equation of excess Gibbs energy, we can play around this to having the rearranged Gibbs energy or partial Gibbs energy over RT equal to ln activity coefficient. And then by using the expression of summability relation, which is the thermodynamic property equal to its composition times the partial properties. So we can obtain the excess Gibbs energy over RT equal to the summation of the composition to the ln activity coefficient of ln gamma. So referring to the Gibbs to Hahn, which the summability at constant temperature and pressure, so we can have another expression or known, okay, this equation known as the Gibbs-Duhem equation, okay, by calculating the composition times the with the ln activity coefficient and sum up all the species equal to 0 at constant temperature and pressure. So to be more understand, maybe we can take a look on the example. So determine the excess Gibbs energy. So GE for a binary mixture. Okay, the binary mixture temperature is given, pressure also given, the mole fraction of component 1. So we have the first extract of the information. Mole fraction of component 1 is 0.18. So component 2 is 0.82 in the liquid phase and 0.5. Okay, vapor phase is 0.5. So Y2 equal to 0.5. P saturation for both species also given. Okay, from the equation, second is describe the equation to be used. So GE over RT equal to the summation of this SI ln gamma I, or activity coefficient for I. So we can use this equation to determine the Gibbs energy. So first we need to determine the gamma. Or gamma, that's mean we can refer to the modified Ross law. So to determine the gamma, we have the correlation of Y or P equal to X1, gamma 1, P1 saturation. So gamma 1 equal to over S1 P1 saturation. So Y1 is 0.5, P is 0.25 bar, and then we have S1 is 0.18, and saturation is 0.2 bar. So since all the unit is standardized, so we can determine the answer is 3.47. Okay, and then we proceed to the component 2, Y2P, S2, P2 saturation, 0.5, 0.1, so we have 0.82, 0.1. So let me check 0.25. So this is supposed to be 0.25. And then the answer is 1.52. So you may insert to, okay, the third is insert to the equation. So GE over RT. So we have the S1 is 0.18 times gamma 1, 3.47 plus 0.82, 1.52. So GE equal to 0.567 times R is 14 joule per mole dot K. So the temperature is 60 plus 270 K. And then the answer is 1571 joule per mole. So equivalent to 1 kilojoule per mole. So this is how we determine the excess Gibbs energy. Okay, in summary, the fugacity can be determined for pure species. You may use this equation, and then you can also obtain the activity coefficient. So in obtain the activity coefficient, you may refer to the pressure. If P higher than 15 bar, so you may use the Lee-Kessler. Or if less than 15 bar, so you may use the Varier equation. So for the mixture, we have two mixture, whether mixture in gas or in liquid. Okay, for the mixture in liquid, so you may use this. Okay, this is the excesses which involved with the solution. Okay, and then as the last to conclude that liquid mixture behavior are revealed through excess properties. So we can reveal the liquid mixture behavior based on the excess Gibbs energy and excess enthalpy or excess properties. Okay, the excess properties is depend on the temperature, but normal temperature are not strongly influenced by pressure, although they have diverse behavior but common features. So for all excess properties equal to 0 when the pure species is obtained in the system. So the excess Gibbs energy versus the composition or the component 1 is approximately parabolic. Okay, basically it refers to this graph. So we have this excess Gibbs energy. Basically it has the parabolic. But for both HTS, because G equal to H minus TS, so that's why we consider the enthalpy and TS as a big individualistic composition dependency. Okay, when the excess property has a single sign, the extreme value for the excess properties, or whether maximum or minimum, often occur near to the equimolar. So actually it always occurs at equimolar. So as conclusion, the theory of solution thermodynamics, we already covered the potential of the chemical potential. The fugacity is to measure the chemical potential by adjust the pressure, and we also determine the fugacity coefficient or the theta equal to the fugacity over the pressure. And then both fugacity and fugacity coefficient can be measured whether in pure species or gas mixture. And then the activity coefficient is introduced if involved with the excess property of solution of liquid. By comparing the ideal and the real, we denote as or describe by the excess properties. Okay, as to prove your attendance, or you may try to answer this. What is the excess properties? Choose any thermodynamic relation properties to express the excess properties. Okay, by end of that explanation, I ending my presentation. So next topic, we will focus more on the application or relates to the Gibbs excess property over RTO. We can relate it to the actual data. How can we determine the properties using the experimental data? Okay, thank you for your attention.